Hello, YouTube fan. Get ready for an amazing video experience. We're thrilled to present to you our video dedicated to linear independence. Enjoy. In the theory of vector spaces, a set of vectors is said to be if there exists no non-trivial linear combination of the vectors that equals the zero vector. If such a linear combination exists, then the vectors are said to be. These concepts are central to the definition of dimension. A vector space can be of finite dimension or infinite dimension depending on the maximum number of linearly independent vectors. The definition of linear dependence and the ability to determine whether a subset of vectors in a vector space is linearly dependent are central to determining the dimension of a vector space. Get ready for a thought-provoking discussion as we delve into definition and its impact on our understanding. A sequence of vectors vk from a vector space is said to be linearly dependent if there exists scalars a k, not all zero, such that of a curve k0, where 0 denotes the zero vector. This implies that at least one of the scalars is non-zero, say as 0, and the above equation is able to be written as a math 1 alfraka e a math 2 a dot alfraka ko a math k if k1 and 0 if k1. Thus, a set of vectors is linearly dependent if and only if one of them is 0 or a linear combination of the others. A sequence of vectors Vn is said to be linearly independent if it is not linearly dependent, that is, if the equation of and of n0 can only be satisfied by a I0 for I1, and this implies that no vector in the sequence can be represented as a linear combination of the remaining vectors in the sequence. In other words, a sequence of vectors is linearly independent if the only representation of 0 as a linear combination of its vectors is the trivial representation in which all the scalars I are 0. Even more concisely, a sequence of vectors is linearly independent if and only if 0 can be represented as a linear combination of its vectors in a unique way. If a sequence of vectors contains the same vector twice, it is necessarily dependent. The linear dependency of a sequence of vectors does not depend on the order of the terms in the sequence. This allows defining linear independence for a finite set of vectors. A finite set of vectors is linearly independent if the sequence obtained by ordering them is linearly independent. In other words, one has the following result that is often useful. A sequence of vectors is linearly independent if and only if it does not contain the same vector twice and the set of its vectors is linearly independent. Without further ado, let's move on to the topic of infinite case. An infinite set of vectors is linearly independent if every non-empty finite subset is linearly independent. Conversely, an infinite set of vectors is linearly dependent if it contains a finite subset that is linearly dependent, or equivalently, if some vector in the set is a linear combination of other vectors in the set. An indexed family of vectors is linearly independent if it does not contain the same vector twice, and if the set of its vectors is linearly independent. Otherwise, the family is said linearly dependent. A set of vectors which is linearly independent and spans some vector space forms a basis for that vector space. For example, the vector space of all polynomials in over the reals has the infinite subset as a basis. Let's now venture into the realm of geometric examples and explore the fascinating intricacies it holds. U and V are independent and define the plane PU. V and W are dependent because all three are contained in the same plane. U and J are dependent because they are parallel to each other. U, V and K are independent because U and V are independent of each other and K is not a linear combination of them or, equivalently, because they do not belong to a common plane. The three vectors define a three-dimensional space. The vectors are null vector, whose components are equal to 0 and k are dependent symptoic. In the next phase, we'll be immersing ourselves in the realm of geographic location and exploring its real-world applications. A person describing the location of a certain place might say, "It is 3 miles north and 4 miles east of here." This is sufficient information to describe the location because the geographic coordinate system may be considered as a two-dimensional vector space ignoring altitude and the curvature of the Earth's surface. The person might add, the place is 5 miles northeast of here. This last statement is true, but it is not necessary to find the location. In this example, the 3 miles north vector and the 4 miles east vector are linearly independent. That is to say, the north vector cannot be described in terms of the east vector, and vice versa. The third 5 miles northeast vector is a linear combination of the other two vectors, and it makes the set of vectors linearly dependent. That is, one of the three vectors is unnecessary to define a specific location on a plane. Also note that if altitude is not ignored, it becomes necessary to add a third vector to the linearly independent set. In general, linearly independent vectors are required to describe all locations in dimensional space. Without further ado, let's move on to the topic of the zero vector. If one or more vectors from a given sequence of vectors vk is the zero vector 0, then the vector vk are necessarily linearly dependent and consequently, they are not linearly independent. To see why, suppose that I is an index i.e. an element of k such that vi0. Then let I1 alternatively, letting I be equal any other non-zero scalar will also work, and then let all other scalars be 0 explicitly. This means that for any index j other than I, i.e. for ji, let a j0 so that consequently a of j of j0. Simplifying over of k gives over of k00 eve I00 eve I0. Because not all scalars are 0 in particular, I0, this proves that the vectors vk are linearly dependent. As a consequence, the zero vector cannot possibly belong to any collection of vectors that is linearly independent. Now consider the special case where the sequence of vk has length 1, i.e. the case where k1. A collection of vectors that consists of exactly one vector is linearly dependent if and only if that vector is 0. Explicitly, if there's any vector then the sequence which is a sequence of length 1 is linearly dependent if and only if alternatively, the collection is linearly independent if and only if 0. As we progress, let's shine a spotlight on linear dependence and independence of two vectors and examine its intricate interplay within our topic. This example considers the special case where there are exactly two vector u and v from some real or complex vector space. The vectors u and v are linearly dependent if and only if at least one of the following is true. 1. U is a scalar multiple of v explicitly. This means that there exists a scalar c such that u or 2. V is a scalar multiple of u explicitly. This means that there exists a scalar c such that v q. If u0, then by setting c0 we have v 0 u. This equality holds no matter what the value of v is, which shows that 1 is true in this particular case. Similarly, if v0 then 2 is true because vu. If uv for instance, if they are both equal to the 0 vector 0 then both 1 and 2 are true by using c1 for both. If u then u0 is only possible if c0 and v0. In this case, it is possible to multiply both sides by a fract to conclude a frac. This shows that if u0 and v0 then 1 is true if and only if 2 is true, that is, in this particular case either both 1 and 2 are true and the vectors are linearly dependent, or else both 1 and 2 are false and the vectors are linearly independent. If u but instead u0 then at least one of c and v must be 0. Moreover, if exactly one of u and v is 0 while the other is non-zero, then exactly one of 1 and 2 is true with the other being false. The vectors u and v are linearly independent if and only if u is not a scalar multiple of v and v is not a scalar multiple of u. Let's now turn our attention to vectors in and examine its role within the larger context. 3 vectors. Consider the set of vectors 1, 1, 3, 2, and 2, 4. Then the condition for linear dependence seeks a set of non-zero scalars such that a begin matrix I and a matrix plus a begin matrix I and a matrix plus a begin matrix I and a matrix begin matrix I and a matrix, or A begin matrix 1 and minus 3 and 1 and 2 and I end matrix begin matrix I end matrix begin matrix I end matrix. Row reduce this matrix equation by subtracting the first row from the second to obtain a begin matrix 1 and minus 3 and 0 and 5 and I end matrix begin matrix I end matrix begin matrix I end matrix. Continue the row reduction by I dividing the second row by 5 and then I multiplying by 3 and adding to the first row, that is a begin matrix 1 and 0 and 0 and 1 and I end matrix begin matrix I end matrix begin matrix I end matrix. Rearranging this equation allows us to obtain a begin matrix 1 and 0 0 and I end matrix begin matrix I end matrix begin matrix I end matrix a begin matrix I end matrix, which shows that non-zero I exists such that 2 4 can be defined in terms of 1 1 and 3 2. Thus, the three vectors are linearly dependent. Two vectors. Now consider the linear dependence of the two vectors 1 1 and 3 2 and check. A begin matrix I end matrix plus a begin matrix I end matrix a begin matrix I end matrix or a begin matrix 1 and minus 3 1 and 2 end matrix begin matrix I end matrix a begin matrix I end matrix. The same row reduction presented above yields a begin matrix 1 and 0 0 and I end matrix begin matrix I end matrix begin matrix I end matrix. This shows that I0, which means that the vectors v equal 1 1 and v equal 2 are linearly independent. Get ready for an enlightening exploration as we dig into vectors in R and understand its role in the broader context. In order to determine if the three vectors in a begin matrix I end matrix a begin matrix I end matrix a begin matrix I end matrix are linearly dependent, form the matrix equation. A begin matrix I end matrix begin matrix I end matrix equal begin matrix I end matrix. Row reduce this equation to obtain a begin matrix 7 and 0 and 0 and I end matrix begin matrix I end matrix equal begin matrix I end matrix. Rearrange to solve for v and attain a begin matrix I end matrix begin matrix to end matrix equal a begin matrix I end matrix. This equation is easily solved to define non-zero I where it can be chosen arbitrarily. Thus, the vectors v and v are linearly dependent. In this section, we'll be exploring alternative methods using determinants. An alternative method relies on the fact that n vectors in N are linearly independent if and only if the determinant of the matrix formed by taking the vectors as its columns is non-zero. In this case, the matrix formed by the vectors is a begin matrix I end matrix. We may write a linear combination of the columns as E lambda a begin matrix I end matrix begin matrix lambda a lambda I end matrix. We are interested in whether for some non-zero vector. This depends on the determinant of A, which is deta 1 to 1 3 5 0. Since the determinant is non-zero, the vectors 1 1 and 3 2 are linearly independent. Otherwise, suppose we have meters vectors of n coordinates, with m and then there is a matrix and is a column vector with meters entries, and we are again interested in a 0. As we saw previously, this is equivalent to a list of n equations. Consider the first meters rows of the first meters equations. Any solution of the full list of equations must also be true of the reduced list. In fact, if is any list of meters rows, then the equation must be true for those rows. I'm 0. Furthermore, the reverse is true. That is, we can test whether the meters vectors are linearly dependent by testing whether deta I am 0 for all possible lists of meters rows. In case mn, this requires only one determinant, as above. If mn, then it is a theorem that the vectors must be linearly dependent. This fact is valuable for theory. In practical calculations, more efficient methods are available. Now, let's shift our perspective and explore more vectors than dimensions from a different angle. If there are more vectors than dimensions, the vectors are linearly dependent. This is illustrated in the example above of 3 vectors in A. In this part of the video, we'll be diving deep into natural basis vectors and unraveling its profound impact. Let V run and consider the following elements in V, known as the natural basis vectors. A begin matrix marf1 and equal and l.so marf2 and equal and l.so marf n and equal and l.so end a matrix. Then en are linearly independent. Let's now turn our attention to linear independence of functions and examine its role within the larger context. Let V be the vector space of all differentiable functions of a real variable t, then the functions it and b's in V are linearly independent. Let's zoom in on proof and understand its implications. Suppose A and B are 2 real numbers such that at beat 0. Take the first derivative of the above equation. At A beat 0. For values of t we need to show that A 0 and B 0. In order to do this, we subtract the first equation from the second, giving beat 0. Since x is not 0 for some t, B 0. It follows that A 0 too. Therefore, according to the definition of linear independence, et and x are linearly independent. In the following section, we'll be immersing ourselves in the captivating world of space of linear dependencies. A linear dependency or linear relation among vectors is a tuple with scalar components such that of n of n0. If such a linear dependence exists with at least a non-zero component, then the vectors are linearly dependent. Linear dependencies form a vector space. If the vectors are expressed by their coordinates, then the linear dependencies are the solutions of a homogeneous system of linear equations, with the coordinates of the vectors as coefficients. A basis of the vector space of linear dependencies can therefore be computed by Gaussian elimination. In the upcoming section, we'll be shining a light on affine independence. A set of vectors is said to be affinely dependent if at least one of the vectors in the set can be defined as an affine combination of the others. Otherwise, the set is called affinely independent. Any affine combination is a linear combination, therefore every affinely dependent set is linearly dependent. Conversely, every linearly independent set is affinely independent. Consider a set of meters vectors Vm of size n each, and consider the set of meters augmented vectors left right of size n1 each. The original vectors are affinely independent if and only if the augmented vectors are linearly independent. As we progress, let's zoom in on linearly independent vector subspaces and examine its role in shaping our overall narrative. 2 vector subspaces M and north of a vector space X are said to be if Mn. More generally, a collection MD of subspaces of X are said to be if MIK for every index I, where KMK MI1 MD, MK for all K span K, I1 K. The vector space X is said to be of MD if these subspaces are linearly independent and MDX. Leave a comment below and let me know what you thought of this video.